Somewhere in deep space, a dying star collapses into a point smaller than an atom. Around it, a black hole tears open. Light falls in and never comes back. You imagine that whatever crosses that edge is simply gone forever. But the greatest minds in physics uncovered something far stranger. When a black hole slowly fades and disappears, it takes a secret with it. And that missing secret could shatter the deepest rule in all of science, the rule that says the past can never be erased. Together we will chase a glow no one saw coming, a wall of fire that should be impossible, and tiny wormholes woven from pure connection. If a mystery this strange pulls you in, tap like and subscribe, and journey with us to the edge of reality. One question waits at the bottom of every black hole. Take a breath. We begin. Picture a smooth, invisible line floating in empty space. Nothing marks it. No wall, no fence, no colour. Cross it, and your story ends. This line wraps around every black hole. Scientists call it the event horizon. It is the true edge of the trap. A black hole forms when a giant star runs out of fuel and crushes itself down. Gravity wins. The star's whole weight folds into a space smaller than a city, then smaller than a town, then smaller than a marble. Around that crushed point, gravity grows so fierce that it bends the path of everything nearby. Rocks fall in, gas falls in, even light, the fastest thing in the universe, falls in and cannot climb back out. The event horizon is the exact spot where escape becomes impossible. Outside it, a fast rocket could still fight its way free. 1 inch inside it, no rocket ever built could save you. No engine is strong enough. No speed is high enough. The exit simply closes. Here is the strange part. If you floated toward that edge, you would feel nothing special at the moment you crossed. No jolt, no warning bell, no sudden pain. The horizon has no surface to touch. You would sail across a boundary that looks like ordinary black sky. Think of a slow river drifting toward a waterfall you cannot see. The water feels calm. The current feels gentle. Then, without a single sign, you pass the last point where swimming back would work. You keep drifting, smiling, unaware. The edge already caught you. That is a black hole's horizon, a quiet trap with no walls and no bottom that you can spot. Scientists have watched this happen from a safe distance. In the year 2019, a team pointed telescopes across the whole planet at once and captured the first real picture of a black hole. They saw a glowing ring of hot gas circling a pit of pure darkness. That dark centre was the horizon, the shadow of a monster 40 billion miles wide sitting in a galaxy far beyond our own. For a long time, people believed the event horizon was the whole mystery, a door that only opens inward, a gate that swallows and never gives back. But the horizon is only the beginning of the puzzle. It hides a deeper secret underneath. The real riddle is not the edge. It is what waits at the centre and what happens to everything that reaches it. Because a black hole does not just capture things, it seems to keep them forever in a place our science cannot follow. Your body, your ship, every atom you are made of, all of it would rush toward one single point buried at the core. And that point breaks the rules. Every law we trust about matter, energy and time starts to crack the closer you get. Our best equations, the ones that guide rockets and predict eclipses, begin to spit out answers that make no sense at all. So the question grows, what actually happens to you once you cross that silent line? Where do you go? What do you become? To find out, we have to do the one thing no scientist could ever survive. We have to jump in. Get ready. The fall is about to begin, and time itself is going to betray you. So you leap. Feet first into the dark, toward the edge no one returns from. At first, nothing feels wrong. You drift. Stars glide past. The black hole grows in front of you like a hole punched into the sky. Your heart pounds, but your body feels normal. Then time starts playing tricks. Imagine a friend stayed behind on a distant space station, watching you fall through a powerful telescope. To that friend, something bizarre happens. You appear to slow down. The closer you drift to the horizon, the more you crawl. Your falling body freezes like a video stuck on one frame. Your friend would watch you hover at the edge for 1,000 years, for 1,000,000 years. You would seem to hang there, glowing dimmer and dimmer, redder and redder, until you fade from sight completely. To the outside universe, you never quite cross. You just slowly vanish, painted onto the edge like a fading photograph. But that is only their view. From inside your own ship, time feels totally normal. Your watch ticks at its usual pace. You do not freeze, you do not slow, you sail right across the horizon in a single calm second and keep going down. Two people, two clocks, two completely different stories about the same fall. Gravity this strong stretches and warps time itself, so fast and slow depend on where you stand. Now the danger arrives. The pull at your feet is stronger than the pull at your head, because your feet are closer to the centre. On Earth, this gap is tiny and harmless. Near a black hole, it grows monstrous. Your feet get yanked harder than your head. Your body starts to stretch. Scientists gave this a grim nickname. They call it spaghettification. You would be pulled thin and long, like a strand of pasta drawn out of dough, then thinner, then longer, every atom in your body dragged into a screaming line pointing straight at the core. The size of the black hole decides how fast this horror hits. Fall into a small one, and you get shredded before you even reach the horizon. Fall into a giant one, the kind sitting in the heart of galaxies, and the stretching stays gentle at first. You could cross the edge whole, alive, still breathing, with the real destruction waiting deeper inside. Either way, the path leads to one place, the very centre, a single point where all the crushed matter piles up. And that point is where everything we understand falls apart. Picture our best map of gravity as a smooth, reliable machine. It steers spacecraft. It predicts the swing of planets. It has passed every test for 100 years. But push that machine toward the centre of a black hole and it jams. It sputters. It hands you an answer that means nothing. The equations say the density there becomes endless, infinite. Gravity climbs to infinity. Space squeezes to a size of 0. And infinity is the sound of physics screaming that it is lost. No scientist has ever seen this centre. No signal escapes it to tell us the truth. We only have the math, and the math surrenders. So what is really down there at the bottom of the fall? A speck? A door? A wound in reality itself? The name we give it sounds simple. The truth behind it is anything but. At the very bottom of the fall waits a single point. Scientists call it the singularity. The word sounds clean. The thing it describes is a nightmare for physics. A singularity is a place where all the matter that fell in gets crushed into a space with no size at all. 0 width, 0 height, 0 everything. Yet it still holds the full weight of a collapsed star, or a million collapsed stars stacked together. Try to picture that. Take a whole star, heavier than our sun, and squeeze it down past the size of a planet, past the size of a mountain, past the size of a grain of sand, until it has no size left to shrink into. That is what our equations demand. Infinite squeezing, infinite density, a dot heavier than worlds. Nothing in nature should behave this way. And that is the warning sign. When a scientist runs a calculation and the answer comes back as infinity, it almost never means the universe truly holds something infinite. It means the tool being used is broken. The map has run off its own edge. Think of an old car dashboard. The speed needle climbs and climbs, then slams into a peg at the far end and stops. The car is not going infinitely fast. The gauge just cannot measure any higher. The singularity is that pegged needle. Our theory of gravity hit its limit and locked up. For most of the last century, one idea ruled how we understand gravity. It came from a famous set of equations describing how mass bends space and time. Those equations are stunningly accurate. They guided landers to distant moons. They predicted the bending of starlight during an eclipse, exactly on the mark. Scientists trust them completely for almost everything. But those equations were built for the smooth, wide world. Planets, stars, whole galaxies. They assume space is a gentle sheet you can bend and stretch. The singularity is not smooth or wide. It is the tiniest possible place. And down at that scale, a different set of rules takes over. The rules that govern atoms and the particles inside them. Those two rulebooks have never agreed. The gravity rules and the atom rules work perfectly in their own zones. Ask them to work together, right at the singularity, and they collide like two trains on one track. The math produces garbage. Answers that read as infinity, or as nonsense, or as nothing at all. So the honest truth is this: nobody knows what a singularity really is. We do not even know if the point is truly a point. Many scientists suspect the infinity is a lie, a placeholder, a sign that something deeper is hiding there, something we have not discovered yet. Maybe a new kind of physics smooths it out. Maybe the matter never fully crushes to zero, and instead reaches some strange minimum size. Maybe the centre holds a door to somewhere else entirely. Each idea sounds wild, and each one is still on the table because we have zero data from inside. The singularity is a locked room with the lights off, and every key we own breaks in the lock. Yet even this broken centre is not the strangest thing about black holes. There is a rule so deep, so trusted, that a black hole seems to snap it in half. A rule about memory, about whether the past can ever truly be erased. Every branch of science leans on one quiet promise: information is never destroyed. That sounds small. It is one of the biggest ideas we have. Here is what it means. Take anything in the universe: a book, a snowflake, a person, a star. It is made of particles arranged in a very specific pattern. That exact pattern, every detail of what a thing is made of and how its pieces move, counts as information. The promise says that pattern can be scrambled, hidden, burned, or blown apart, but it can never be wiped out for good. The details always survive somewhere, in some form, even if they are impossible to read. Let me show you with fire. Suppose you toss a page of writing into a campfire. The paper curls, blackens, and turns to ash and smoke. To your eyes, the words are gone forever. The message looks destroyed, but physics disagrees. Every particle of that page still exists. The smoke carries some, the ash holds the rest, the heat and light spread the rest into the air. In theory, if you could track every single atom, every puff of smoke, every glow of light, with perfect care, you could piece the whole page back together and read the original words. Nothing truly vanished. The message just got scrambled into a form too messy for any human to follow. The information stayed complete. This is the deep law. Scientists build almost everything on top of it. It sits underneath the rules of atoms, the rules of heat, the rules of chemistry. Break it, and huge pieces of science stop making sense. Why does the promise matter so much? Because it makes the universe honest. It means the present remembers the past. Think of it like a movie you can run backward. If information never dies, then in principle you could take the universe as it is right now, hit rewind, and watch every event unhappen in perfect order, all the way back to the beginning. The scrambled details would unscramble. The ash would lift back into a page. The past is always still written into the present, hidden but whole. That backward movie is the heart of the promise. The universe never forgets. It cannot forget. Every cause leaves a mark that lasts. For a long time, scientists felt safe with this law. It held up in every experiment. Smash particles together in a giant machine, and you can still account for everything that goes in and comes out. Nothing goes missing. The books always balance. Then black holes walked in and kicked the table over. A black hole eats things: stars, gas, light, maybe a careless spaceship. All of it crosses the horizon and rushes down to that broken centre. Once it is inside, no signal from it ever reaches us again. The object is sealed away behind the point of no return. So the frightening question grows. When a black hole swallows a page of writing, is the information really still there, hidden inside? Or does the black hole do the one thing the universe swore was impossible? Does it erase the past for real? For decades, most scientists shrugged. The stuff is trapped inside, they figured, safe behind the horizon, scrambled but alive. The books still balance, just out of reach. Then one man discovered something about black holes that no one expected. Something that turned this comfortable answer into a full-blown crisis. Black holes, it turned out, do not last forever. Before we meet the man who broke everything, sit with the promise a little longer. Because to feel the shock of what is coming, you have to feel how solid this rule really was. Information survives. Always. That was the bedrock. Let me sharpen why scientists clung to it. Imagine the universe as a giant machine full of moving parts. Every particle follows clear rules as it bumps and spins. Those rules have a special quality. They work forward in time, and they work backward in time, both directly. That means the state of everything right now was built from exactly one past, and it will roll into exactly one future. No details get added from nowhere. No details drop into nowhere. The total record stays exactly the same size, forever. Scientists tested this idea in the most violent way they could invent. They built machines miles wide that smash particles together at nearly the speed of light. In year after year of crashes, they tracked the wreckage. Every time the pieces added up, whatever went in could be found again in what came out. The universe kept perfect books, so people trusted the promise the way you trust the ground under your feet. Now here is the twist that makes black holes so scary. Their whole nature seems designed to snap this rule. A black hole hides its center behind the horizon. Whatever falls in gets locked away from the rest of the universe. From the outside, you can never again read the details of what went down. The object is gone from view. For a while, that seemed fine. Locked away is not the same as destroyed. A letter sealed in a vault is still a letter. The information could be hiding inside the black hole, scrambled but whole, waiting behind a door we simply cannot open. As long as the black hole exists, the vault stays shut, and the promise stays technically safe. The books still balance. The record still lives, sealed at the core. But that comfort rests on one huge assumption. It assumes the vault lasts forever. It assumes the black hole never opens, never leaks, never dies. Picture a safe at the bottom of the ocean, holding the only copy of a priceless message. As long as the safe sits there, sealed and solid, the message survives. Unreachable, yes, but real. You could tell yourself the words are still in there. Now imagine the safe slowly dissolves. The metal thins, the walls crumble to dust, the safe disappears completely, and when it is gone, you check the seabed, and the message is nowhere. Not inside because there is no inside anymore. Not floating free because you never saw it come out. Where did the words go? That is the trap black holes were about to spring. Everyone assumed the vault was eternal, so nobody worried about the message. The seal would hold for all time. Problem avoided. Then one scientist proved the vault is not eternal at all. He showed that black holes leak, they shrink, they fade, and one day they vanish entirely, taking the sealed vault with them. The moment the vault can disappear, the sealed message has a terrifying problem. If the black hole is gone, and nothing readable ever came out, then the record is broken. The past is erased. The deepest promise in science lies shattered on the ocean floor. His name was Stephen Hawking, and his discovery started as a whisper of light at the edge of the dark. In the 1970s, a young scientist named Stephen Hawking asked a simple question. What happens right at the edge of a black hole, where gravity meets the tiny world of particles? The answer he found rocked physics to its core. Hawking discovered that black holes are not completely black. They glow, faintly, quietly, but truly. A black hole gives off a whisper of light and heat, all on its own, leaking energy into space. At first, this sounds impossible. The whole point of a black hole is that nothing escapes. Light falls in and stays, so how can light also come out? The trick lives in the strange rules of the very small, and to picture it, you have to change how you think about empty space. We imagine empty space as pure nothing, a blank, still void. But the rules of particles say otherwise. Even in the emptiest gap between stars, space is quietly fizzing. Tiny pairs of particles pop into being for a flash, then crash back together and disappear. They blink in and out, everywhere, all the time. This bubbling happens even where there is nothing at all. Think of a glass of clear soda that looks perfectly still. Lean in close, and you see tiny bubbles forming and vanishing all over. Empty space is like that soda. Calm from far away, fizzing up close. Now bring this fizzing right up to the edge of a black hole. A pair of particles pops into being just at the horizon. Normally, the two would find each other again and vanish, cancelling out, leaving nothing behind. But at the horizon, the black hole plays dirty. Sometimes one of the pair drifts inside the edge and falls in. Its partner, still outside, has no one to cancel with. So instead of vanishing, that lonely particle escapes into space, flying away as real light. To a far-off telescope, it looks like the black hole gently breathed out a spark. Do this over and over, across the whole horizon, and the black hole shines with a soft, steady glow. Scientists named it Hawking radiation, after the man who found it, and it is widely accepted as real physics, worked out with careful math, even though the glow is far too faint for us to detect from any black hole we know. That faintness matters. A big black hole glows so weakly that its light is colder than the coldest empty space. You could never spot it. But the glow is there, sipping tiny bits of energy away, second after second, year after year. And here is the part that changes everything. That escaping energy is not free. It has to come from somewhere. The only bank account a black hole has is its own mass. So every spark of glow costs the black hole a crumb of its weight. The black hole is paying for its own light. Slowly, patiently, it is spending itself away. Which means a black hole is not the eternal, unchanging monster everyone imagined. It has a leak, a slow drip that never stops. Given enough time, that drip drains the whole thing. The vault at the bottom of the sea has started to dissolve. So what happens as a black hole keeps shrinking, spark by spark, closer and closer to nothing at all? The answer only gets stranger and faster. Let us slow down and really watch the glow being born, because this quiet process is the seed of the whole crisis. Return to the fizzing edge of the black hole. Pairs of particles keep flickering into life all along the horizon. Most blink out again in an instant, harmless and unseen. But every so often the horizon splits a pair. One partner tumbles inside, the other shoots away as a spark of real light. That escaping spark is a piece of Hawking radiation, a crumb of the black hole's glow. Focus on the partner that fell in. This is where the deep trouble hides. The two particles in a pair are born linked. They share a strange connection, a bond that ties their fates together no matter what. Scientists call this bond entanglement, and it is one of the most tested and confirmed facts about the tiny world. Linked particles act like two ends of the same coin. Flip one, and you instantly know the other. Now the black hole rips the coin in half. One end flies free into space, the other end plunges past the horizon, lost inside forever. The spark that escapes carries a problem. On its own, it looks random, empty. It seems to hold no real message about whatever the black hole ate long ago. It's just a faint, plain flicker of light, still secretly linked to a partner trapped inside. Multiply this by an unimaginable number. A black hole gives off these sparks endlessly, over billions of years. Each one flies out looking blank and random. Each one leaves its linked partner behind the edge. Slowly the black hole shrinks. Every escaped spark carried away a tiny bit of its mass. The monster is dieting against its will, growing smaller each moment. Here is the pattern that should worry you. All the details of whatever fell in, the writing on that page, the shape of that ship, the memory of that star seem to stay locked deep inside. Meanwhile, the only thing leaving is a steady stream of blank sparks that appear to know nothing about any of it. Imagine a giant library slowly burning, one book at a time, and the only thing floating out the windows is plain grey smoke. The smoke does not carry the words seem to stay inside right up until the whole building collapses. If that is truly what happens, the promise is in mortal danger. Blank smoke cannot rebuild a library. Random sparks cannot rebuild a page. For years this looked like a puzzle we could wave away. Surely, people thought, the escaping light secretly carries the information somehow, hidden in a pattern too subtle to see. Surely the books still balance. But the deeper scientists looked at Hawking's own careful math, the worse it got. The glow really did seem blank. It really did seem to carry nothing back out. The details really did seem stuck inside, waiting to be destroyed when the black hole finally died, and the black hole was going to die. That was the new undeniable fact. A leaking vault cannot last, so the sparks keep flying, the black hole keeps shrinking, and a countdown begins, ticking toward the moment the whole thing disappears. What happens in that final flash, when the last of the black hole burns away? That ending is where the crisis explodes into full view. A black hole is dying from the moment it's born. It just dies with almost unbelievable patience. The glow we met earlier drains it, spark by spark. But this draining has a cruel twist in its timing, and that twist decides the fate of everything inside. Start with a big black hole, the kind that sits in the centre of a galaxy, heavier than millions of suns. Its glow is unbelievably faint. It leaks energy so slowly that in a human lifetime it barely changes at all. The bigger the black hole, the weaker the glow, and the longer it clings to life. How long can it last? The numbers are almost meaningless to a human mind. A large black hole could keep glowing and shrinking for a length of time so vast that it dwarfs the current age of the universe many times over. Star after star will burn out, whole galaxies will go dark, and the black hole will still be there, sipping away its mass, one faint spark at a time. But it is shrinking. That is the key. It never stops shrinking. And here comes the twist. As a black hole loses mass, its glow gets stronger, not weaker. A smaller black hole burns hotter and faster, so the dying speeds up as it goes. Think of a spinning top losing energy. For a long while it spins smoothly, barely slowing. Then, near the end, it wobbles harder and harder, faster and faster, until it suddenly clatters flat in a wild final burst. A black hole dies the same way, slow for almost forever, then a violent rush at the very end. In its last moments, the black hole is tiny, smaller than a room, smaller than a marble, and it is glowing furiously now, pouring out energy in a rising scream of light. Then comes the final flash. In one last burst, the black hole releases its remaining energy all at once and vanishes completely. Where a monster once sat, there is now empty space. The vault has fully dissolved. The safe on the seabed is gone, and this is the exact moment the crisis becomes impossible to ignore. Rewind through the black hole's whole life. It ate stars, gas, light, maybe a page of writing, maybe a ship. All those details rushed inside and got locked away. Over the ages, the black hole glowed, sending out a river of sparks that all looked blank and random, carrying no clear message about what it had swallowed. Now the black hole is gone, vanished in that final flash. There is no inside anymore, no vault to hold the sealed details, no door left to open someday. So where did the information go? If it went out with the sparks, we cannot see how, because the sparks looked empty the whole time. If it stayed inside, it just got destroyed, because the inside no longer exists. Either way, the honest math seemed to say the same grim thing. The details are gone, truly gone, erased, and erased is the one word the universe was never supposed to allow. A page burned in a fire can be rebuilt from the smoke and ash. A page swallowed by a black hole that later vanishes leaves nothing to rebuild from. The backward movie of the universe hits a blank frame and stops. Two of our deepest theories were now pointing at the same spot and screaming opposite answers. The stage was set for a war. Now the trap snaps shut. Two of the greatest ideas in all of science stand face to face, and they cannot both be right. This clash earned a famous name. Scientists call it the black hole information paradox. For nearly 50 years it has haunted the smartest minds alive, and it still is not fully solved. Let us lay the two sides out plainly, because the whole rest of our journey grows from this single fight. On one side stands the promise from the tiny world of particles. Information is never destroyed. Ever. Whatever exists now can always, in principle, be traced back to what came before. The universe keeps perfect books. This rule has passed every test we can throw at it. On the other side stands Hawking's own careful work on black holes. His math said the escaping glow is blank. It carries no memory of what the black hole ate. So when the black hole finishes glowing and vanishes, the swallowed details vanish with it. Gone. Destroyed. Read those two sides again. They flatly contradict each other. One says destruction is impossible. The other says a black hole destroys. They cannot both stand. This is a true paradox. A place where our best knowledge folds in half and points two ways at once. And it is not a small crack in a corner of science. It sits under the foundations of physics itself. Feel the weight of it. If Hawking's glow really erases information, then the promise is false. And if that promise is false, then the deepest rules of the tiny world are broken. Those same rules run every atom in your body, every chemical reaction, every spark in your brain. Shaking that promise shakes everything built on top of it. Picture two master builders arguing over one house. The first builder swears the foundation is solid stone, unbreakable, tested for a century. The second builder points at a crack running straight through that same stone and says the whole thing is crumbling. They are looking at the same house. They cannot both be telling the truth, yet each one has ironclad proof. That is the position physics found itself in. Two towering theories, each proven again and again in its own territory, now colliding head-on over a single question. What happens to the stuff inside a black hole? Hawking himself first came down hard on one side. He argued that black holes really do destroy information, and that the beloved promise would simply have to fall. For years he defended this view fiercely. If a black hole says the past can be erased, he reasoned, then maybe the past can be erased. Most of the particle scientists refused to accept that. Giving up the promise felt like giving up the ground under science. There has to be a way out, they insisted. The information must escape somehow. We just cannot see the trick yet. The argument grew so heated that two famous scientists once made a public bet about it, with the fate of information as the prize. The whole field split into camps, and the strangest part is this. To even hope to solve the fight, scientists could not just study one theory or the other. They had to force the two enemies to work together. They had to build a bridge between the rules of gravity and the rules of the tiny world. That bridge did not exist yet. Building it would take decades, and it would lead to ideas far weirder than the paradox itself. The first step was to understand why these two giants had been at war from the very start. To understand why a black hole breaks physics, you have to meet the two rule books running the universe and see why they cannot stand each other. The first rule book governs the big: stars, planets, galaxies, and gravity itself. It describes how heavy things bend the space and time around them, the way a bowling ball dips a stretched sheet. This rulebook is smooth, gentle, and beautifully exact. It has guided space probes across billions of miles and never once failed. The second rulebook governs the small, atoms and the tiny particles that build them. Down at this scale, the world stops being smooth and gets jumpy, fuzzy, and full of chance. Particles blur into clouds of maybe. They pop in and out of empty space. They link across distance in ways that feel like magic. This rulebook too has passed every test, powering the screens and chips inside every phone on Earth. Each book is a masterpiece. Each rules its own kingdom without a single defeat. The problem is simple to say and brutal to fix. The two books describe the same universe using languages that do not translate. One is smooth, the other is jumpy. One deals with the huge, the other deals with the tiny. In everyday life they never have to meet, because nothing is both enormously heavy and impossibly small at the same time. A star is heavy but big, so only the gravity book matters. An atom is tiny but light, so only the particle book matters. The two kingdoms stay politely apart, and everything works. Then a black hole appears and drags them into the same room. A black hole is monstrously heavy, which demands the gravity book, but its centre is crushed to a size smaller than an atom, which demands the particle book. For the first time, one object is both giant and tiny at once. Both rulebooks slam down on the table and start shouting different answers. Think of two expert map makers. One draws only oceans in flowing blue curves, the other draws only cities in sharp square grids. Each map is perfect for its own world. Now ask them to draw a single map of a city built on the water, streets flooding into waves. Their styles crash. The lines do not line up. The map turns to nonsense right where the two worlds meet. The centre of a black hole is that flooded city. It is the one place where the huge and the tiny cannot avoid each other. And there, the two rulebooks produce that scream of infinity we met before, the sign that both have failed at once. For a century, scientists have hunted for a single master rulebook that could contain both, a theory that describes gravity and particles in the same breath. They call this dream a theory of everything. Bits and pieces exist. A full working version still does not. The information paradox is the sharpest edge of this whole war. It is the exact spot where the smooth book and the jumpy book give opposite verdicts about the fate of a page swallowed by darkness. So to make progress, scientists needed a fresh clue, a hint about how a black hole truly stores what it eats, and that clue arrived from an unexpected direction, from a young researcher who asked a childlike question. What if a black hole is not as forgetful as everyone assumed? For a long time, scientists believed a black hole was the simplest object in the universe. Strange, since it swallows such complicated things. They summed this belief up with a funny phrase: "A black hole has no hair. Here is what that means. Take two totally different objects and drop them into a black hole. Drop a dead star made of iron, drop a mountain of diamonds, drop a library of books or a fleet of ships, anything you like. Once each one falls in, the black hole barely changes. It grows a little heavier, and that is almost the whole story. From the outside, all a black hole shows you is a tiny handful of numbers, how much it weighs, how fast it spins, and whether it holds an electric charge. That is it. 3 plain facts. Everything else about what fell in seems to wash away completely. The iron and the diamonds and the books all leave the exact same trace, which is almost no trace at all. 2 black holes built from wildly different meals can look absolutely identical from outside. Same weight, same spin, same nothing else. That is the no-hair idea. A black hole shaves off every detail of its history and keeps only 3 plain numbers. It is the ultimate act of forgetting. Picture a giant machine that shreds anything you feed it into identical grey pellets. Feed it a painting, and out come grey pellets. Feed it a phone book, and out come the same grey pellets. Stand at the machine's exit, and you could never guess what went in. Every input becomes the same dull output. For years, this felt like a clean and tidy fact. Simple black holes, described by 3 numbers, easy to write on a napkin. Scientists were almost proud of how plain they seemed. But now, armed with the information paradox, that same tidy fact turns into a nightmare. If a black hole truly erases every detail of what it eats, keeping only weight, spin, and charge, then the swallowed information is not hidden. It is gone, wiped clean at the door, and that smashes the promise that information can never be destroyed. So the no-hair idea forced a brutal choice. Either it is wrong, and black holes secretly remember far more than 3 numbers, or the promise is wrong, and the universe really can forget. Most scientists bet against the plain picture. They suspected the no-hair idea was only skin deep. It described how a black hole looks from far away, using the smooth gravity rule book. But it might completely miss what happens right at the edge, where the jumpy particle rules take over. Maybe a black hole is bald on the outside and secretly covered in fine, invisible hair up close. Maybe every detail of what fell in leaves a faint mark somewhere on the black hole, too subtle for the old smooth equations to catch. If that were true, the information would not be destroyed at all. It would be written down, hidden in plain sight on the black hole itself. But written down where exactly? A black hole has a crushed centre we cannot reach, and a wide dark edge that swallows everything. Which part could possibly hold the memory of every star and ship it ever ate? One scientist found a stunning clue, and it pointed at the last place anyone expected, the surface. The clue came from a young scientist named Jacob Bekenstein, and it started with a worry about heat. Bekenstein noticed something that bothered him deeply. If black holes truly erase everything, they would break another trusted rule, a rule about disorder and heat that scientists guard almost as fiercely as the promise itself. That rule says disorder in the universe always grows. Mess never cleans itself up for free. A shattered glass never leaps back together. Heat always spreads from hot to cold, never the reverse. This one-way flow is one of the most reliable patterns in all of nature. Now imagine dropping a hot, messy, disorderly object into a black hole. If the black hole erases it completely, then all that disorder just disappears from the universe. And that is not allowed. You cannot make mess vanish. The rule forbids it. Bekenstein saw only one way out. The disorder must not vanish. It must get stored inside the black hole somehow, which means a black hole must have its own hidden supply of disorder, its own secret measure of how much stuff it has swallowed. Scientists have a word for that measure of hidden disorder. They call it entropy. The more entropy something has, the more hidden detail it holds, the more ways its tiny parts could be arranged without changing how it looks outside. So Bekenstein made a bold claim. A black hole must carry entropy. It must secretly count everything that fell in. And then he asked the winning question. If a black hole stores hidden information, where does that storage live? How much can it hold? His answer stunned everyone. He found that a black hole's hidden information does not depend on its volume, on how much room is inside. It depends on the area of its surface, the size of the horizon wrapping around it. Stop and feel how strange that is. Think about a normal storage space, like a warehouse. How much can it hold? That depends on the space inside, the volume. A bigger inside means more room for boxes. That is common sense for every container you have ever seen. A black hole breaks that common sense. Its storage does not scale with the room inside. It scales with the outer surface, the skin. Make the surface bigger, and the black hole can remember more. The memory lives on the edge, spread across the horizon like writing on a wall. Picture a library where none of the books sit on shelves inside the building. Instead, every word is written on the outer walls, packed tight across the surface. Want to store more books? You do not need a bigger inside. You need bigger walls. The whole record hides on the boundary. This was the first real hint at where a black hole's memory might live. Not lost in the crushed center. Not erased at the door. Spread across the horizon itself, the very edge we thought was empty. Bekenstein's idea, later sharpened by Hawking's own math on the glow, tied three things together into one shocking package. A black hole's surface area, its hidden information, and its temperature all march in lockstep. And that link between surface and memory would grow into one of the boldest ideas in the history of science. An idea suggesting our entire universe might be a kind of illusion painted on a distant wall. Let us press deeper into Bekenstein's shock, because the link between surface and memory hides a secret about reality itself. Recall the strange finding. A black hole's hidden information grows with its surface area the size of its horizon, and not with the room inside. Double the skin, and you double the memory. The record lives on the edge. Now watch what this does when a black hole eats. Every time something falls in, the black hole grows a little. Its horizon swells, its surface area gets bigger, and by Bekenstein's rule, its hidden information ticks up by exactly the right amount to account for whatever it's swallowed. The surface keeps a running tally written across the edge, item by item, so the horizon behaves like a vast sheet of paper wrapped around the darkness. Each thing that falls in leaves a mark on that sheet. The marks are unimaginably tiny and packed unimaginably tight, far too fine for us to read. But by this picture, they are there. The black hole remembers on its skin. How tight is the packing? Almost beyond belief. The information a black hole can store on its surface is the densest storage allowed anywhere in nature. You could not cram more detail into that space if you tried. A black hole is the most crowded hard drive the universe permits. Here is a way to feel the scale. Imagine covering the horizon in the smallest possible squares, each one almost inconceivably tiny, far smaller than an atom, far smaller than the parts inside an atom. Each little square holds a single crumb of information. Count all the squares tiling that huge surface, and you get the black hole's full memory. The bigger the surface, the more squares, the more it remembers. This tight surface storage carries a jaw-dropping suggestion, one that reaches far past black holes. If all the information about everything inside a black hole can be written on its two-dimensional surface, then maybe the inside is, in some deep sense, not the fundamental thing. Maybe the true record lives on the boundary, and the inside is just a projection of that boundary, the way a flat sheet of writing can describe a solid room. Scientists gave this breathtaking idea a name, the holographic principle. You've seen a hologram, those shiny stickers that show a full three-dimensional image, even though the sticker itself is flat. All the depth, all the solidity, is encoded in a thin, flat surface. Tilt it, and a whole scene seems to pop out of a sheet with no real depth at all. The holographic principle says our universe might work the same way. The full, solid, three-dimensional world we live in could be described completely by information, stored on a distant two-dimensional boundary. The room is real to us, yet the master copy is painted on the wall. Black holes handed scientists this wild idea, and it turned into one of the most powerful tools in modern physics. It hinted that gravity and the shape of space might be built out of something more basic, some pattern of information living on a surface. If that is true, then solving the black hole paradox is not a side quest. It is a doorway into what space and reality are actually made of, but a doorway is not a solution. Knowing the memory might live on the surface still does not tell us how it escapes when the black hole dies. So the hunt pushed on, into the horizon itself. The holographic idea is so strange that it is worth standing still inside it, because it flips how you picture everything around you. Look at the world. It has depth. You can walk forward, reach out, move up and down. 3 directions, 3 dimensions, solid and real. Nobody doubts it. Now the holographic principle whispers a shock. All the true information describing this deep solid world might actually be stored on a flat boundary far away, with no depth of its own. The depth you feel could be a kind of readout of that flat record. The way a movie's whole world lives inside a thin strip of film. Black holes are what forced this idea into the open. Remember the lesson from the surface. A black hole crams its entire memory onto its horizon, a 2-dimensional skin. Everything it ever swallowed, every detail of every star and ship gets written on that edge. The inside adds no extra storage at all. Scientists took that lesson and asked a daring question. What if this is true not just for black holes, but for every region of space? What if any chunk of the universe can be fully described by information living on the surface that wraps around it? That leap is the holographic principle in full. It says the amount of information inside any region is set by the area of its boundary, never by the volume within. The wall holds the whole story. The inside is the projection. Let me make the strangeness concrete. Picture a sealed room. Inside sit tables, people, air, light, all the busy 3-dimensional stuff of a real place. The holographic principle claims you could throw away the inside entirely and lose nothing, as long as you kept a perfect record written on the room's walls. From that flat wall record, the entire solid room could be rebuilt exactly down to the last detail. The room is the shadow. The wall is the truth. This sounds like fantasy. It grew into serious, respected science, because it gave researchers something priceless. A shortcut. Here is why it became so powerful. The rules of gravity inside a region are fiendishly hard to solve. The rules of particles on a flat boundary with no gravity at all are far easier to handle. The holographic principle hinted that these 2 descriptions are secretly the same thing, written in 2 languages. A hard gravity problem inside equals an easier particle problem on the edge. That means a scientist stuck on a brutal gravity puzzle could translate it into a friendlier boundary puzzle, solve that instead, and translate the answer back. A locked door in one room, opened with a key from another. For the information paradox, this was gold. The paradox is a gravity problem, tangled and infinite. But on the flat boundary, the rules are the trusted particle rules, the ones that swear information can never be destroyed. If the inside and the boundary are truly the same story, then whatever the boundary says must also be true inside. And the boundary is crystal clear. On the boundary, information always survives. Always. No exceptions. So the holographic principle handed scientists a bold prediction. If the 2 pictures really match, then information must escape a dying black hole after all, no matter how impossible it looks from the inside. The promise, it seemed, might be saved, but saying information escapes and showing how it escapes are 2 very different things, and the how led straight into a wall of fire. Before we reach the fire, let us follow one tempting escape route in full, because it feels like it should solve everything, and its failure teaches us the most. Here is the hopeful idea. If a black hole's memory lives on its surface, then maybe the escape is simple. As the black hole glows and shrinks, maybe each spark of light peels off the surface and carries a little of that stored memory away with it. Picture the horizon as a wall covered in tiny writing, every mark a detail of something swallowed. Now the black hole glows, and each escaping spark grabs a few marks off the wall as it leaves. Spark by spark, the writing lifts off the surface and flies into space. When the last spark departs, the wall is bare, the black hole is gone, and all the writing has safely escaped. The promise holds, case closed. It is a beautiful picture. For a while, it gave scientists real hope. The information sits on the edge. The glow comes from the edge. So let the glow ferry the information out, clean and tidy. But when scientists checked this idea against the hard math, it hit a brutal snag. Remember how the sparks are born. Each escaping spark comes from a pair split by the horizon. One partner flies out, the other falls in, and the 2 are linked by that deep bond, the entanglement we met before. The outgoing spark is not free and blank. It is tied to a partner now trapped inside the black hole. That link is the trouble. For the escaping glow to carry real information about what the black hole ate, the sparks would need to be linked to each other, weaving the swallowed details into a shared pattern as they leave. But Hawking's math says each spark is linked instead to its lost inside partner, not to the other sparks. So the outgoing glow cannot spell out the message. Its links point the wrong way, back into the darkness. Worse, there is a strict rule about these bonds. A single particle can only share its deepest link with one partner at a time. Scientists call this rule monogamy, like a bond that refuses to be split 3 ways. A spark cannot be fully linked to its inside partner, and also fully linked to the outgoing glow. It has to choose. So the simple picture breaks. If the sparks stay linked to their inside partners, the way Hawking's math demands, then they leave blank, and the memory never gets out. If instead the sparks link up to carry the memory, then their bond with the inside partners must snap. And snapping that bond is not free. Breaking these deep quantum links releases energy. A lot of it. Follow that thread, and something horrifying appears at the edge of the black hole. To let information escape by breaking all those inside links, the horizon would have to blaze with energy. The smooth, calm edge we described at the very start, the one you could cross without feeling a thing, would instead become a raging sheet of fire. That collides head-on with everything we believed about falling in. A big black hole's horizon was supposed to feel like empty space. Ordinary, gentle, crossable in a calm second. Now the math was hinting at something monstrous waiting exactly there. A barrier of pure energy, hot enough to incinerate anything that touched it. Scientists gave this terrible possibility a name that fits it perfectly: the firewall. And it forced the cruelest choice in the whole story. The firewall is one of the most disturbing ideas in modern physics, because it attacks something we thought was safe. The simple act of falling through a horizon. Go back to the calm picture from the start of our journey. You drift toward a giant black hole. You reach the horizon, the edge of no return, and you feel nothing. No jolt, no heat, no wall. Space looks ordinary. You sail across in a quiet second, whole and alive, with the real danger waiting far below at the centre. That gentle crossing was one of the most trusted ideas about black holes. The smooth gravity rulebook demands it. At the horizon of a big black hole, that rulebook insists space should look perfectly normal, empty, boring, safe to cross. The firewall says the opposite. It says you would slam into a wall of raging energy at the horizon and burn away in an instant, destroyed the moment you touch the edge. Where does this fire come from? From the cruel choice we uncovered. To save the promise, to let information escape the dying black hole. Scientists found they might have to break the deep links between the outgoing sparks and their trapped inside partners, and breaking those links floods the horizon with energy. Enough energy to build a sheet of fire around the whole black hole. So physics landed in a nightmare with 2 doors, and both doors are terrible. Behind the first door you keep the smooth, gentle horizon. Falling in feels calm and normal, just as the gravity rulebook swears. But to keep that calm edge, you must leave the inside links unbroken, which means the glow leaves blank, which means the information is destroyed. You save the peaceful fall and lose the promise. Behind the second door, you save the promise. Information escapes, the books balance, the tiny world's rules hold firm. But the price is the firewall. The horizon becomes a lethal sheet of flame. Falling in no longer feels calm. It kills you at the edge, and it violates the gravity rulebook that swore the horizon was ordinary. Read those 2 doors again. One breaks the promise about information, the other breaks the promise about smooth space. Each door shatters a rule scientists were desperate to keep, and you must walk through one of them. Picture standing before 2 levers. Pull the first, and the universe forgets, tossing out its most sacred rule about memory. Pull the second, and every black hole edge in existence becomes a hidden bonfire, betraying everything the gravity book promised about gentle horizons. There is no lever that keeps both rules whole. That is the trap. This firewall puzzle exploded through the world of physics. It took the old information paradox, already 50 years deep, and sharpened it into something even nastier. Now the fight was not only about a dying black hole far away, it was about what you would feel crossing any horizon, right there at the edge. Scientists split into fierce camps. Some accepted the firewall and its fire. Some clung to the smooth horizon and searched for a loophole. Some suspected the whole setup hid a mistake in how we think about inside and outside, and that last group tugged at a thread so strange it bends the mind. What if the inside story and the outside story of a black hole were never supposed to be told at the same time? What if reality itself refuses to let you check both? Faced with the fire, some scientists reached for an escape so bold it sounds like a trick. Maybe the whole paradox rests on a mistake nobody noticed. Maybe we assumed we could know two things at once that the universe forbids us to know together. This idea has a name, complementarity, and it asks you to think about a black hole in a completely new way. Here is the setup. The firewall trap comes from following two observers at the same time. One person falls into the black hole, another person stays safely outside watching. The paradox appears when you try to write down what both of them see side by side in one shared story. Complementarity says stop right there. That shared story is the mistake. You're never allowed to combine both viewpoints into one. Nature only ever lets you stand in one place at a time. Think about what each observer sees. The person who stays outside watches the falling friends slow down, freeze at the horizon, and smear across the edge as a fading glow, exactly as we saw long ago. From outside, everything that falls in gets stuck on the surface and eventually leaves with the black hole's glow. The information never truly goes inside. It rides the edge and escapes. For this outside watcher, the promise is safe. The person who falls in sees something totally different. They cross the horizon in a calm second, feeling nothing, and sail down toward the center. For this falling observer, the information goes in with them, smooth and whole, no fire, no freezing. Now here is the daring claim. Both stories are completely true. The information is on the surface, and the information is inside. It sounds like a flat contradiction. Complementarity says it is only a contradiction if a single observer could check both at once, and no observer ever can. Why not? Because to see the outside story and the inside story together, you would have to be in two places at the same time, outside watching and inside falling, and you simply cannot. If you fall in, you can never send a message back out to compare notes. If you stay out, you can never reach inside to check. The two viewpoints are sealed off from each other forever. No single person can ever catch the universe telling two different tales. Picture a coin spinning on a table. From above, you see one face. From below, you see the other. Both faces are real. But you can never see both faces at the very same instant from a single spot. You have to choose a side. Complementarity says a black hole is like that coin. Inside story or outside story, pick one, and you can never peek at both together to catch a clash. For a while, this felt like a clever rescue. If the two stories can never be checked side by side, then the contradiction never truly appears, and both the smooth horizon and the promise survive. No fire needed. But the firewall argument was built to attack exactly this escape. It tried to show a way that one clever observer could, in principle, catch the two stories clashing by examining the outgoing glow very carefully and then diving in. If that were possible, complementarity would fall and the fire would return. The fight ground to a standstill. Both sides had strong arguments. Neither could land the final blow. The paradox held its ground, older than ever, still unbeaten. What physics needed now was a hard number, a precise, undeniable calculation that could prove which side was right, a curve drawn from pure math that would settle whether information escapes at all. That curve was coming, and it would change everything. A quiet scientist named Don Page found the test that could end the whole fight. He did it with a single shape. Here is the idea behind it. As a black hole glows, it sends out a stream of sparks. Those sparks and the black hole left behind grow tangled together, sharing hidden links, the same deep bonds we met before. Page asked a simple question. How tangled do they get as time goes on? The answer splits the two sides of the war cleanly apart. Follow Hawking's math first. If every spark leaves blank and random, then the tangle between the escaping glow and the black hole just keeps climbing, higher and higher, spark after spark, all the way until the black hole vanishes. Then, in the final flash, the black hole is gone, and all the tangle has nowhere to connect. It ends broken. On a graph, this looks like a line that rises forever, then snaps. Now follow the promise instead. If information truly escapes, the story has to end differently. When the very last spark leaves, the black hole is gone, and everything it ever ate now floats outside as light. At that point, nothing is hidden anymore. The whole record is out in the open, readable, and if everything is readable, the tangle must be back down to zero at the end. So the tangle cannot rise forever. It has to climb for a while, reach a peak, and then fall back down to zero as the black hole fades. On a graph, that traces a smooth mountain, up one side, over the top, down the other. That mountain shape has a name. Scientists call it the Page Curve. Picture two hikers describing the same trail. One swears the path only goes up, climbing until it falls off a cliff. The other swears it rises to a summit and then comes back down to the valley floor. Same trail, two completely different maps. Whichever map is right tells you how the journey truly ends. The Page Curve is that second map, the one with the summit, and it became the sharpest test in the whole paradox, because the shape of that line is a yes or no answer. If the real tangle only ever rises, information dies, and Hawking wins. If the real tangle rises and then falls, tracing the mountain, information escapes, and the promise wins. For decades, this was the dream target. Draw the true curve from honest math, and you would know which side reality was on. No more arguing, no more guessing, just the shape. There was only one problem: nobody could compute it. To draw the real curve, scientists needed to track those hidden links through the fire of a black hole, using both rulebooks at once, the smooth and the jumpy working together. And those two books still refused to cooperate. Every attempt jammed on the same old wall between gravity and the tiny world. So the Page Curve sat there for years, a clear target that no one could hit. Everyone knew the shape that would save physics. No one could prove nature actually drew it. The mountain had a peak, and that peak marked a special moment in a black hole's life. A turning point. A halfway tipping point where the whole story flips. To understand the rescue that was coming, we first have to stand on that summit. The peak of the Page Curve marks a strange and special moment. Scientists call it the Page Time. It is the instant a black hole's story flips from hiding to revealing. Let us build up to it slowly, because this turning point is the hinge the whole rescue swings on. A fresh black hole is full of secrets. It has swallowed stars, gas, maybe a page of writing, and all those details sit locked inside. In its early life, the black hole glows, but the sparks that leave are far too few to spell out everything hidden within. The black hole is still holding most of its secrets close. During this first stretch, the tangle keeps rising. Each new spark adds to the hidden links between the outgoing glow and the black hole. The mountain path climbs. More light escapes, more tangle builds higher and higher. Then comes the halfway point, the Page Time. This is the moment when the black hole has glowed away about half of itself. Half its mass is gone, radiated into space as light. And something flips at exactly this point. The black hole crosses over from being a keeper of secrets to being a leaker of secrets. Before the Page Time, the escaped light is too little to rebuild what fell in. After the Page Time, enough light has escaped that, in principle, the outgoing glow starts carrying the hidden details out into the open. The tangle stops climbing. It reaches the summit and begins to fall. Why does the flip happen right at the halfway mark? Think of it like a conversation between two people passing notes. As long as one person holds most of the notes, the other cannot reconstruct the full message. But the instant the notes are split evenly, and then tip past halfway, the second person starts holding enough to piece the whole thing together. The balance of secrets shifts. That shift is the Page Time. Before it, the black hole knows more than the escaped glow. After it, the escaped glow knows more than the black hole. The summit of the mountain sits exactly where the two are even. Here is a way to feel the scale of it. For a big black hole, The page time comes after a mind-bending stretch of years, longer than the current age of the universe by a huge amount. The turning point is real, but it waits almost unimaginably far in the future. Half a black hole is a lot of glowing to do. Once past that peak, the path heads downhill. Spark by spark, the tangle falls. The black hole shrinks toward nothing, and the hidden record steadily spills out into the light until the final flash empties the last of it. The tangle reaches zero. The mountain returns to the valley floor. Information saved. That is the shape physics needed to prove. A climb, a summit at the page time, and a fall back to zero. For years it stayed a beautiful guess. Scientists could describe the mountain in words. They could not draw it from the raw laws of gravity, because the two rule books still would not work together. To finally hit the target, they needed a bridge between those books, a place where gravity and the tiny world could be written in the same language and actually calculated. That bridge turned out to be an entire imaginary universe, sealed inside a box. To force gravity and the tiny world to work together, scientists tried a clever trick. They built a toy universe simple enough to fully control. This toy universe lives inside an imaginary box. Its space is curved in a special way, gently bending back on itself, so that anything travelling outward eventually feels a wall far away and returns. Nothing escapes to infinity. The whole universe sits neatly contained, like a fish in a round bowl. Why trap a universe in a bowl? Because a sealed box is far easier to study than the wild open cosmos. With walls to lean on, the math becomes tame enough to actually solve. Scientists could run the numbers without everything flying off to infinity and breaking. Now comes the beautiful part, the part that turned this toy into a treasure. This boxed universe has an inside and an edge, the wall of the bowl, and scientists discovered a stunning link between the two. Everything that happens inside the box, including gravity, including black holes, can be described perfectly by a different set of rules living only on the edge. Rules with no gravity at all, just particles dancing on the boundary wall. This is the holographic principle made real, sharpened into a working tool. The inside of the bowl, with all its bending space and its black holes, is one language. The flat wall of the bowl, with its simple particles, is another language. And the two languages say exactly the same thing. Every event inside has a matching event on the edge, and the other way around. Scientists call this link a dictionary. It translates between the hard language of gravity inside and the easy language of particles on the wall. Picture a snow globe. Inside, a tiny three-dimensional town sits under falling snow, with depth and buildings and streets. Now imagine that every detail of that town, every window and rooftop, was secretly written in code around the glass rim of the globe. Read the rim, and you know the whole town. Change the town, and the rim writing changes to match. The rim and the town are two versions of one thing. That is the boxed universe. The wall is the rim, the inside is the town. And the dictionary lets you swap between them at will. For the information paradox, this was the breakthrough tool everyone had waited for. Here is why. On the flat wall, the rules are the trusted particle rules, the ones that swear information is never destroyed. On the wall, there is no paradox at all. Information always survives, plainly and simply. But the wall describes the exact same universe as the inside. So whatever happens on the wall must also be the truth inside, where the black hole lives. And on the wall, the answer is clear. Information escapes. Always. No exceptions. This meant scientists could finally prove which way the argument went, at least inside this toy universe. Build a black hole in the box. Let it glow and shrink. Watch what the wall says. And the wall, speaking its simple particle language, insists the information comes back out. The promise, in this boxed world, was safe. The books balanced. The mountain shape had to be real. But knowing the answer is right is not the same as seeing how it works. To draw the actual page curve, scientists needed to dig into the strangest object the dictionary revealed. A bridge made of pure connection, linking two distant things through a secret tunnel. Inside the boxed universe, scientists uncovered something almost too strange to believe. a hidden tunnel built out of nothing but connection. To see it, we have to return to the deep bond we keep circling back to, the link between particles, the one scientists call entanglement. Recall what entanglement does. Take two particles, born linked, and separate them. They stay tied together in a way that ignores distance. Measure one, and you instantly learn about the other, even if they sit on opposite sides of a galaxy. The bond does not weaken with distance, it just holds. For decades, this link felt like a ghostly thread, a spooky connection with no substance, no shape, no location in space. Two dots, tied by an invisible string that runs through nowhere. Then a pair of scientists noticed a jaw-dropping match. The math that describes two deeply linked particles looks almost identical to the math that describes a wormhole. A tunnel through space connecting two far-apart places. Sit with how wild that is. A wormhole is a bridge in the fabric of space itself, a shortcut linking here to there. Entanglement is a bond between tiny particles. These sound like completely separate things from completely separate rulebooks, yet their math lines up, point for point. So the scientists made a daring proposal. Maybe these two things are secretly the same. Maybe every pair of deeply linked particles is joined by a tiny wormhole, a bridge too small and too strange for us to travel through, but real all the same. The ghostly thread of entanglement might be an actual tunnel, woven into the shape of space. The idea got a short nickname from the initials of the scientists involved, but you can just hold the picture. Linked particles are wormholes, connection is a bridge. Picture two distant islands with no boat between them. From above, they look completely cut off, separated by miles of ocean. Now imagine that hidden deep under the water runs a tunnel joining them, carved through the seabed. From the surface, you would never guess it was there. Yet the two islands are truly connected, linked by a passage below. Entanglement, this idea says, is that hidden tunnel between particles. This flips how we picture the deep bond. The link is no longer a spooky thread through empty nothing. It is a piece of shape, a bridge, part of the geometry of space itself. And that leads to a thought so bold it reshapes reality. If every link is a tiny bridge, then space might be stitched together out of these bridges. All the connection in the universe woven into tunnels might be what holds the fabric of space in one piece. For the black hole paradox, this was the missing key. Remember the trouble. Each escaping spark stays linked to a partner trapped inside the black hole. Those links look like a curse, the very thing that seemed to doom the information. But if every link is secretly a bridge, then all those trapped partners are connected to the outgoing glow by hidden tunnels. And a hidden tunnel is a way out. Maybe the information inside is joined to the light outside by these secret bridges. Maybe the inside was never truly sealed off at all. To use that key, scientists had to learn how connection builds shape, how the tunnels weave space itself. The idea that linked particles are tiny bridges leads somewhere breathtaking. It suggests that space itself might be woven out of connection. Let us take that slowly, because it changes what you think the world is made of. We usually treat space as the empty stage. It is just there, the backdrop where stars and planets act out their lives. Space is the container, and stuff sits inside it. That is how everyone pictures it. Solid, simple, given. The new idea turns this upside down. It says space might not be the given stage at all. Space might be built, stitched together out of countless tiny links between particles. The connection comes first. The shape of space comes out of it. Here is how to picture the stitching. Imagine a huge piece of cloth. From far away it looks like one smooth, solid sheet. Lean in close, and you see the truth. The cloth is made of thousands of tiny threads, all woven together. Pull the threads tighter, and the cloth holds firm. Cut the threads, and the cloth falls apart into loose scraps. Space, this idea says, is that cloth. And the threads are the deep links between particles. Where particles are strongly linked, the threads are tight, and space is smooth and connected. Where the links are cut, the threads snap, and space itself tears into disconnected pieces. Scientists tested this thought inside the boxed universe. They found that if they slowly removed the links between particles on the wall, the space inside the box began to come apart. Two regions that were smoothly joined would drift into separate pieces as the links between them vanished. cut enough threads, and the fabric of space ripped in two. That was a shock. It meant the smoothness of space depends on connection. Take away the linking, and space stops being one solid thing. The stage falls apart into scraps, so connection is the glue of reality. Every stretch of smooth space, every gentle distance between 2 points, rests on a web of hidden links holding it together. The world feels solid because the threads are pulled tight. Now bring this back to the black hole, and the pieces start to click. A black hole is drenched in these links. The sparks flying out stay tied to their partners inside. By the new picture, those ties are threads, tiny bridges stitching the inside of the black hole to the glow outside. The interior and the escaping light are woven together by connection, and that weaving hints at the escape route. If the inside of the black hole is stitched to the outside light by a web of hidden bridges, then the inside is not a sealed vault after all. It is sewn onto the outside world by threads, and along those threads, information might travel out. This gave scientists a completely fresh way to attack the paradox. Instead of asking how a spark carries a message across the horizon, they could ask a deeper question. Which parts of the universe are stitched to which other parts? Where do the threads lead? Answer that, and you would know where the black hole's hidden record truly lives. Not by tracking sparks, but by mapping connection. To turn that idea into hard numbers, scientists built a new tool, a way to find the exact surface where the threads matter most. A counting trick buried deep inside the black hole. To find where a black hole's memory hides, scientists invented a precise new tool. It sounds technical at first. The picture behind it is simple. Start with the question they needed to answer. When light escapes a black hole, how much hidden information does that light really carry? To draw the page curve, they had to measure this exactly at every moment of the black hole's life. The old way of measuring gave Hawking's answer. It said the escaping glow carries no real information, and the tangle only ever rises. That answer led straight to the destroyed promise. Everyone suspected it was missing something. The new tool works differently. Instead of just counting the sparks as they leave, it searches for a special surface, hidden somewhere in or around the black hole. This surface marks the true boundary of what the outside world can secretly know. Let me unpack that with a picture. Imagine the black hole and its glow as a vast tangled web of threads, the connection threads from before. The outside light holds one end of countless threads. The other ends reach into the black hole. To measure how much the outside truly knows, you have to find the right place to cut the web. Cut it in the smartest spot, and you count the fewest threads. That smallest cut tells you the real amount of hidden information. The tool's job is to find that smartest cut, the surface where the web is thinnest. Scientists hunt across every possible surface, in and around the black hole, and pick the one that gives the smallest count. That winning surface reveals the truth about what the outside world can know. Think of it like finding the weakest point in a fence around a field. If you want to know how cut off the field really is, you look for the spot where the fewest wires cross. That thinnest, weakest stretch tells you how sealed the field truly is. The tool does the same for a black hole, searching for the thinnest stretch in the web of connection. For a long while, scientists only knew how to look for this surface in the easy places, near the outer edge of the black hole, and there, the tool gave the old answer. The tangle only rises. Hawking's grim result stood. Then came the twist that cracked everything open. Scientists realized they had been searching too small a space. They had only checked surfaces near the outside, but the tool allows the winning surface to appear anywhere, including deep inside the black hole near the very center. When they let the search reach inside, a brand new surface appeared, one that had been hiding all along, buried deep within the black hole. And for an old, glowing black hole past its halfway turning point, this deep inside surface gave a smaller count than the outer one. A smaller count means the outside knows more than anyone thought. It means the tangle stops rising and starts to fall. That deep surface changed the answer. It bent the rising line back down, exactly toward the mountain shape everyone had been chasing. The page curve, appearing at last from honest math. And this deep hidden surface carved out a region of the black hole's inside so strange it earned a name of its own. a piece of the interior that secretly belongs to the outside world. They called it the island. The new counting tool revealed something that sounds impossible. A chunk of the black hole's inside secretly belongs to the outside world. Scientists named this chunk the island. Take a moment with how bizarre that is. The inside of a black hole is supposed to be the ultimate sealed room. Cross the horizon, and you're cut off from the rest of the universe forever. That was the whole idea from the very first part. The edge you cross once and never return from. The island breaks that wall. It says a piece of the interior floating deep inside the black hole is actually part of the outside. Its secrets belong to the escaping glow. Reach into the outside light, and you are secretly reaching into that inner island too. How can a region be inside and outside at the same time? The answer goes back to the threads of connection. Remember, every spark that escaped stays linked to a partner trapped within the black hole. Over ages of glowing, a mountain of these trapped partners piles up deep inside, and they are all tied by hidden threads to the vast cloud of light now drifting far outside. The island is the region where all those trapped partners live, and because they are so densely woven to the outside glow, the math says they count as part of the outside. The connection is so strong that the inside island and the outside light behave as one single system. Read the light, and you have read the island. Picture a remote village deep in the mountains, cut off by cliffs on every side. No road reaches it. It looks completely isolated. But every single person in that village is on a live video call with family in a distant city, every hour of every day. In every way that matters for sharing knowledge, the village is part of the city. The cliffs seal it off in space. The connection makes it belong somewhere else entirely. The island is that village, sealed by the horizon, yet joined to the outside by so much connection that it counts as outside. And here is why the island saves physics. If the deep interior island belongs to the outside glow, then the information trapped inside is not trapped after all. It is already part of the escaped light, counted in the outside world, safe. When scientists include the island in their calculation, the hidden record of the black hole shows up in the outgoing glow. The tangle, which seemed doomed to rise forever, bends back down once the island joins the count. The mountain forms, the page curve appears, information escapes. For the first time, using honest math from the laws of gravity, scientists had drawn the shape that saves the promise. The summit, the fall, the return to zero. All of it, straight from the equations, once the island was allowed in. It felt like a miracle, a hidden piece of the inside belonging to the outside, rescuing the deepest rule in science. But a miracle this strange demands an explanation. Where did the island come from? Why does the math suddenly allow a chunk of the interior to jump to the outside? The answer hid inside an even weirder calculation, one that summoned ghostly bridges out of the equations themselves, linking copies of the black hole in ways no one saw coming. The island seemed to appear by magic. To trust it, scientists had to know why it showed up. The reason came from one of the strangest calculations in modern physics. To measure hidden information, scientists sometimes use a clever cheat. Instead of studying one black hole, they imagine making several identical copies of it, side by side, and studying them together. The copies are just a math trick, a way to make a hard sum possible. At the end, you squeeze the copies back down to one and read off the answer. For years, everyone assumed the copies stayed separate. Each copy sat alone in its own space, minding its own business, never touching the others. You do the sum with the separate copies, collapse them, and get Hawking's grim result. Information lost. Then scientists looked closer at what the laws of gravity actually allow, and they found something hiding in the math. The copies do not have to stay separate. Gravity permits secret bridges to form between the copies, tunnels, linking one copy of the black hole to another. These bridges were always allowed by the equations. Everyone had simply forgotten to include them. Scientists called these hidden tunnels replica wormholes, bridges between copies, and once you let them into the sum, the whole answer changes. Here is the picture. Imagine you are asked to measure something using several identical photographs of the same room, laid out on a table. For years, you treated each photo as a separate, disconnected image. Then you discover that faint tunnels can open up, joining one photo to the next so that they link into a single connected loop. Suddenly, the photos are talking to each other, and the measurement comes out completely different. That is what happened. The replica wormholes joined the copies into a connected chain, and when the black hole was old, past its halfway turning point, this connected answer beat the old separate one. The bridges won. And here is the beautiful part. When you include the replica wormholes and then collapse the copies back to one, the leftover trace of those bridges, in the single, real black hole, is exactly the island. The ghost bridges between copies are the deep reason the island exists, so the island was never truly magic. It was the shadow of these hidden tunnels, cast into the real world. The connection that lets a piece of the inside belong to the outside comes from bridges the math allowed all along. Feel the strangeness of what this means. To get the right answer about a single black hole, scientists had to imagine many copies of it, secretly joined by tunnels, and let those tunnels do the work. Reality, in some deep sense, seems to know about connections between things that are not even supposed to exist. Most scientists were stunned that it worked at all. The replica wormhole trick gave the page curve cleanly from the raw laws of gravity in the boxed universe. Two separate teams found it at nearly the same time, and the whole field lit up. It felt like the paradox was finally cracking. The mountain had been drawn, the promise looked saved. The information seemed to escape after all. And yet, in the middle of the celebration, a hard truth remained. Drawing the curve is one thing. Explaining how a single page of writing actually climbs out of a black hole is another. And on that question, the math stayed silent. The replica wormhole calculation felt like a triumph. Scientists had drawn the page curve straight from the laws of gravity. The mountain was real. The promise looked safe. Then the celebration ran into a hard wall, a question the math could not answer. Here is the trouble. The calculation proves that information escapes a black hole. It shows the tangle rising, peaking, and falling, exactly the shape that saves physics. It tells you, beyond doubt, that the hidden record comes out, but it does not tell you how. Think about what that means. Imagine a locked safe at the bottom of the sea, holding a message. A brilliant calculation proves with perfect certainty that the message ends up outside the safe. It shows the message must escape, yet it says nothing about the path. No cracked hinge, no secret door, no tunnel through the metal. Just a promise that somehow the message gets out. That is where scientists stood. They had ironclad proof that information leaves the black hole. They had no story for the journey. How does the writing on a swallowed page climb across the horizon and ride the glow into space? The island math stays quiet. It counts the information as outside, but it never shows the escape in motion. This gap matters more than it might seem. Remember the firewall, the wall of fire that threatened anyone crossing the horizon. That whole nightmare came from asking how the information gets out without breaking the deep links or lighting the edge on fire. The island trick sidesteps that question. It proves the book's balance without ever explaining the mechanism, so the old worry in a quieter form is still there. There is another puzzle hiding in the island idea. It asks us to believe that a chunk of the deep interior secretly belongs to the outside world. But if you actually fell into the black hole, you would swear the inside is a normal place, right there around you, solid and present. How can that same region also be, in some accounting, part of the distant glow? The two pictures sit uneasily together, and no one fully understands how they fit. So the replica wormhole result is a strange kind of victory. It is powerful and real. It gave the exact curve everyone chased for decades. Most scientists now believe, more firmly than ever, that information does escape a black hole. The promise is probably safe, yet the deepest why remains open. We can prove the ending. We cannot narrate the middle. We know the message gets out. We cannot trace its steps. And there is one more catch, a big one. Almost all of this progress happened inside the boxed universe, the toy world with walls that bend space back on itself. Our real universe has no such walls. It stretches open, expanding, with no bowl to lean on. Whether these beautiful tricks carry over to the world we actually live in is still an open question. So the crisis is not fully over. It has been pushed into a corner, cornered by clever math, but never finished off. The mountain is drawn, and the mechanism is missing. While most scientists chased the island, others refused to accept that a black hole even has a normal inside. They asked a wilder question. What if there is no smooth interior at all? What if a tiny leftover speck or a tangled ball of string hides the real answer? While many scientists chased the island, others hunted a very different escape. Maybe the black hole never fully dies. Maybe a tiny speck survives, holding everything inside. This idea is called the remnant, and it tries to solve the paradox by refusing to let the vault ever fully vanish. Go back to the heart of the crisis. The terror comes from the final flash, the moment the black hole disappears completely. If the black hole is gone and the glow left blank, then the swallowed record is destroyed. The vault dissolves, and the message with it. The remnant idea says stop the vanishing. What if a black hole shrinks and shrinks but never reaches zero? What if, right at the end, instead of a final flash into nothing, it leaves behind a tiny leftover speck? A crumb of a black hole, unbelievably small, that simply stays. If that speck survives, the crisis softens. Every detail the black hole ever swallowed could stay locked inside that crumb, safe, preserved. The vault never dissolves. It just shrinks to a dot and stays sealed. The message is still in there, so nothing was truly destroyed. The promise holds, in a way. Picture a giant block of ice slowly melting in the sun. Everyone expects it to melt down to nothing, leaving only a puddle. Instead, it melts down to a single pebble-sized core of ice that refuses to melt any further. Frozen inside that stubborn core sits a message, held safe forever. The block is gone. The message is not because the core never fully melted. That stubborn core is the remnant, a speck that will not die, guarding everything inside it for all time. For a while, this felt like a tidy fix. No destruction, no paradox. Just hide the whole record in a crumb that lasts forever. But the remnant idea runs into a brutal problem, and it is a strange one. A black hole can swallow an enormous amount. A giant one eats millions of stars worth of stuff, so the tiny speck left at the end would have to store all of that inside itself. Every detail of millions of stars, packed into a crumb smaller than an atom. That is a monstrous amount of information crammed into an almost nothing-sized space. And most scientists find this deeply troubling. It means these tiny specks could hold nearly unlimited information, despite being nearly weightless and nearly sizeless. Such objects would cause chaos in the rest of physics, popping up in places where the math simply cannot allow that much hidden detail in that little room. Because of this, most scientists doubt the remnant idea. A crumb that holds a whole galaxy of secrets feels like trading one impossible problem for another. The speck saves the promise, then breaks other trusted rules to do it. Still, the idea has never been fully killed. Some version of a leftover, some crumb clinging to the end, remains a live possibility that a few researchers keep alive. But there is a bolder idea still, one that attacks the paradox at its root. What if the mistake was believing a black hole has a smooth, empty inside at all? What if, all the way down, a black hole is something completely different? Some scientists took the wildest swing of all. They said the whole paradox rests on one wrong belief, the belief that a black hole has a smooth, empty inside. Their answer comes from string theory, an attempt to build all of reality out of tiny vibrating threads, and it leads to a black hole that looks nothing like the one we have been picturing. Return to the standard image. A black hole is mostly empty space, wrapped in a horizon, with all its matter crushed into a single point at the very centre. You could fall through the edge, cross a lot of empty room, and only meet trouble at the crushed centre. That empty inside is where the whole paradox breeds, because it hides the information far from the escaping glow. The string theory idea throws that whole picture out. It says there is no empty inside and no crushed central point. Instead, all the way out to the horizon, the black hole is packed solid with a tangled mess of vibrating strings, a dense, fuzzy ball of threads filling the entire space, right up to the edge. Scientists gave this idea a fitting name, the fuzzball. In the fuzzball picture, a black hole has no true horizon to fall through and no empty middle to fall into. The moment you reach the edge, you hit the fuzzy surface of the tangled strings. There is no calm crossing, no empty room, no journey to a distant centre. The surface is the object. It is fuzz all the way through. Picture the difference like two kinds of ball. The old picture is like a hollow glass sphere with a single tiny marble rattling at its centre, surrounded by empty air. The fuzzball is like a ball of yarn, wound tight and solid all the way through, with no hollow space and no centre point at all. Every bit of it is packed with thread. Here is why this solves the paradox. If the black hole is a solid ball of strings, right out to the surface, then the information is not hidden deep in an unreachable centre. It sits woven into the fuzzy surface itself, out in the open, touching the outside world, and when the black hole glows, the sparks come off that surface, carrying the woven details with them. The record escapes naturally because it was on the surface the whole time. No sealed vault, no lost centre, no firewall trap because there is no smooth empty horizon to argue about. The whole problem dissolves if the fuzzball picture is right. It also matches the old clue from long ago, the one about a black hole's memory living on its surface area. A fuzzball is basically all surface, a dense, tangled skin holding every detail of what fell in. The catch is that fuzzballs are fiendishly hard to build in the math. Scientists have managed to construct them fully only for simple, special black holes, not yet for the big, ordinary ones sitting in real galaxies. Whether every black hole is truly a fuzzball remains unproven. It is a bold, beautiful maybe. And notice what the fuzzball dares to suggest, that the inside of a black hole, the vast empty room we have imagined this whole journey, might not exist at all. That thought opens the deepest question in the entire mystery, a question about whether the inside of a black hole is even real. All these strange ideas, the island, the fuzzball, the ghostly bridges, circle one dizzying question. When you reach the bottom of the mystery, you have to ask it, does the inside of a black hole even exist? It sounds like a foolish question. Of course there is an inside. A black hole is a huge object. Cross the edge, and you must be somewhere. There has to be a there, in there. But the deepest ideas in physics keep chipping away at that certainty. Look at what we have seen. The holographic principle says the hole inside might be a projection of information living on a distant surface, the way a solid town can be written on the rim of a snow globe. If that is true, the inside is a kind of image, and the surface is the real thing. The island says a chunk of the deep interior secretly belongs to the outside world, joined by hidden threads. If a piece of the inside is really outside, then what does inside even mean? The fuzzball goes furthest. It says there is no empty inside at all, no room to cross into, just a solid tangled surface. Fall toward it, and you never enter an interior, because there is none. You just meet the fuzz, put these together, and a startling possibility appears. Maybe the smooth, roomy inside of a black hole is a story our old equations tell, an approximation that works from far away but stops being real up close. Maybe the true description lives entirely on the surface, or in the escaping glow, and the interior is a shadow cast by that deeper truth. Picture a rainbow. It looks like a solid arch you could walk up to and touch, but there is no arch there at all. It is a trick of light and water, real to your eyes, yet nothing you can ever reach or stand on. Some scientists wonder if the inside of a black hole is like that rainbow, real to someone falling in, yet not a solid, fundamental place in the deepest description of the world. If that is right, the whole paradox looks different. There was never a sealed vault swallowing information, because there was never a true sealed inside. The information was always out on the surface, or woven into the glow, in plain view of the outside universe. The crisis came from trusting a picture of the interior that was only ever an illusion. But this answer is far from settled, and it clashes with something we feel deeply. If you truly fell into a giant black hole, you would experience the inside as completely real, solid, present. You would cross the edge and float in a genuine space, at least for a while. How can that lived, real experience be reconciled with the idea that the inside is not fundamental? Nobody fully knows. This is the raw edge of the mystery, two truths that both seem right and refuse to merge. The inside feels real to the one who falls. The deepest math hints the inside is a projection. Holding both at once is where the greatest minds in physics now stand, puzzled. The person who started this whole storm spent his life on one side of it, and near the end, after decades of fierce battle, he did something almost no great scientist ever does. He changed his mind and paid up. For years, Stephen Hawking stood firm on one side of the war. He argued that black holes truly destroy information and that the beloved promise would simply have to fall. He believed it so strongly that he turned it into a wager. In the 1990s, Hawking and another scientist, Kip Thorne, made a public bet against a third scientist named John Preskill. Hawking and Thorne bet that information really is lost inside a black hole, gone for good. Preskill bet the opposite, that information always escapes, and the promise holds. The loser owed the winner a prize, agreed upon in writing, for all the world to see. It was a friendly bet with enormous stakes. The fate of one of the deepest rules in science, wagered between famous minds. For years, Hawking defended his side hard. His own math on the globe backed him up. The sparks looked blank. The information looked doomed. If a black hole says the past can be erased, he reasoned, then maybe the past can be erased. He was willing to let the promise fall to save what his equations told him. Then the ground began to shift under him. The boxed universe arrived, with its dictionary linking the inside to a flat wall where information always survives. The holographic ideas grew stronger. Piece by piece, the evidence tilted toward the other side. The wall of the box was clear, and it insisted the promise holds. Information escapes. In the year 2004, Hawking stood up at a big science meeting and did something rare for a scientist of his fame. He publicly changed his mind. He announced that he now believed information does escape a black hole after all. His old answer, he admitted, had been missing something. The promise survives, and he paid his bet. He handed Preskill the agreed prize, a reference book, joking that the winner could extract information from it any time he liked. Think about what that moment took. Hawking had built part of his legend on the opposite claim. He had argued it for decades, yet when the evidence turned, he turned with it, in front of the whole world. That willingness to follow the truth over pride is the real engine of science, but here is the twist that keeps the mystery alive. Hawking conceded that information escapes. He did not, and could not, fully explain how. His change of mind was a bet on where the evidence pointed, more than a finished proof of the mechanism. The deepest how stayed open, exactly the gap we found in the island math. So even the concession was not the end. It was a signal that the tide had turned, that most great minds now believed the promise holds. The war over whether information escapes cooled toward a truce. The war over how it escapes raged on. Hawking spent the rest of his life circling back to black holes, proposing new ideas about soft hidden marks on the horizon, still hunting the mechanism he never nailed down. He died in the year 2018, with the deepest part of his own paradox still unsolved. He had lit the fire 50 years earlier with a simple question about the edge of the dark. The blaze he started is still burning. And that blaze reaches far beyond black holes. It touches the very nature of space and reality itself. You might wonder why so many brilliant people spent 50 years on one strange puzzle about faraway black holes. The answer is simple and staggering. This puzzle is a crack that runs under all of physics. Trace where it leads, and you see the stakes. Start with the promise itself. Information can never be destroyed. This rule sits beneath the science of atoms, heat, chemistry, and every reaction inside your own body. If a black hole could truly erase information, then this rule is not absolute. And if it is not absolute, then the trusted rules of the tiny world have a hole in them. Every prediction built on those rules would carry a hidden crack. The paradox is a test of whether our most basic rulebook can be trusted anywhere at all. Now go deeper to what the rescue ideas revealed. To even attempt a solution, scientists had to accept wild new pictures of reality. That space itself might be woven out of connection, that a solid, three-dimensional world might be a projection of information on a distant flat wall, that linked particles might be joined by tiny bridges, that the inside of a black hole might not be fundamentally real. These are not small tweaks. They are hints about what space, time, and reality are actually made of. And they all came pouring out of one stubborn question about a dying black hole. The paradox turned out to be a doorway into the deepest structure of the universe. Here is the biggest prize of all. Remember the two rule books at war, the smooth one for gravity, and the jumpy one for the tiny world. For a century, scientists have dreamed of joining them into a single master theory that describes everything. That dream is the great unfinished goal of physics. The black hole is the one place those two books are forced to work together, so it is the perfect testing ground for that master theory. Every clue we pull from the paradox, the holograms, the islands, the bridges, is a clue about how gravity and the tiny world finally fit as one. Solve the black hole, and you may have found the seam that stitches the two greatest theories together. Picture a single locked door standing between everything we know and everything we do not. On this side, two beautiful maps of reality that will not line up. On the far side, a single complete map, the theory of everything. The black hole paradox is the keyhole in that door. Peer through it, and you glimpse how the two maps might merge. That is why this matters for you and for everyone. Not because you will ever fall into a black hole, because the answer decides what kind of universe we live in, whether the past is truly permanent, whether space is solid or woven, whether reality is what it seems, or a projection of something deeper we're only starting to see. A question that began with a whisper of light at the edge of the dark grew into a question about the nature of existence itself. And after 50 years of the sharpest minds on Earth throwing everything they had at it, the puzzle still is not fully solved. It stands at the frontier, waiting. One last look at that frontier shows just how much is still unknown and how close we might be. After 50 years, where does this great mystery actually stand? Right at the edge of what humans know, close to an answer yet not there. Let us gather what has been won and what still hides in the dark. Here is what most scientists now believe with real confidence. Information probably escapes a black hole. The promise most likely holds. The past is most likely permanent, even for things swallowed by darkness. The tide turned decades ago, and the island calculation gave it a firm mathematical push. On this point, the field has mostly found peace. But look at how much remains unsolved. Nobody can yet explain how the information physically climbs out of a black hole. The island math proves the record escapes and stays silent on the journey. The mechanism, the actual path the writing takes across the horizon and into the glow, is still missing. We can prove the ending without narrating the middle. Nobody knows for certain whether there is a firewall at the horizon. The wall of fire has been pushed back by the newer ideas, yet it has never been fully ruled out. Whether a giant black hole's edge is calm or blazing is still argued. Nobody knows if the beautiful rescue works in our real universe. Almost all the progress happened inside the toy box with walls, the boxed universe that bends space back on itself. Our cosmos has no such walls. It stretches open and expands. Whether the island trick survives the jump from the box to the real sky is a live and serious question. And nobody knows the biggest thing of all, what a black hole truly is on the inside. Empty room with a crushed center, or solid ball of string, or a projection with no real interior at all. The deepest nature of the object remains a genuine mystery. So the honest picture is a strange mix. A hard-won belief that information survives, wrapped around a thick core of unanswered questions about how and where and what it all means. Picture explorers who have finally proven that a hidden continent exists. They have seen its shape on the horizon. They are sure it is there. But they have not yet landed, not walked its ground, not mapped its rivers or climbed its mountains. They know the destination is real. The journey into it has barely begun. That is where physics stands with the black hole paradox. The destination is in sight. The interior is unexplored. And this is why the puzzle still has the power to break physics. Any real answer, the true mechanism, the final word on the firewall, the fate of the inside, would force a rewrite of the deepest rules we have. It would reshape our picture of space, of time, of information, of reality itself. The crack that started under one dying star could split open the whole foundation and rebuild it stronger. The mystery began with a simple, human question. What happens to the things that fall into the dark? 50 years later, the smartest people alive are still chasing it, armed with holograms and islands and bridges made of pure connection, closing in on an answer that could change everything we think we know. The edge of the black hole is still the edge of human understanding, and out there in the dark, the deepest secret of the universe is still waiting for someone to finally read it.